Today we will discuss the physical meaning of gradient of scalar function, that is physical meaning of gradient of a scalar function, that is grad phi. Grad means gradient, phi means any scalar function, phi is any scalar function, maybe flux. So this grad phi may be written as del phi, because grad means the first order differential part, that is operator ddr of phi, so which is called grad phi. And physically, if we study the physical meaning of the grad phi, then it is nothing, it is just a derivative with respect to the quantity in which the maximum change occurred and the direction along the maximum changes occurred. So we know that del phi means derivative. It is derivative of phi with respect to n. N means it is the change in path in which maximum rate is occurred, and n cap is a normal, or it is a vector or direction which is directed towards the direction in such a way that the rate should be maximum. If we draw the physical meaning or the physical diagram of this equation, then we will get just like any scalar function, let it be phi. At here on the surface the flux is phi, and at this surface flux is phi plus d phi. So there is small change in flux, and let here is origin, and the vector from O to this flux phi is r vector, and O to the second flux is r plus dr vector, and the change from this flux phi to phi plus d phi is dr. So it can be used by triangle of vector additions, that is, this is r, this is dr, and this is the resultant vector. So here at this surface the flux is phi, at this surface flux is phi plus d phi. So the change in flux from here to here, this is change. So change is in such a way that this d phi is d phi upon dn is maximum, or the change is maximum, and n vector a direction, this shows the direction, it shows the magnitude, it is magnitude, it is direction. So n cap is the direction which is in the normal side or perpendicular side, that is, it is direction in such a way that the flux change is maximum, along which maximum change is occurred, So the maximum change is like this one. Now physically we may define the grad phi as this. Phi is scalar quantity. If we consider its gradient, then the gradient of any scalar function is always a vector. The answer is vector overall, it is vector. The gradient of any scalar function is equal to a vector having magnitude, that is, this magnitude is the rate of change of flux with respect to distance, and the direction is towards the where the maximum change is occurred. So this is the physical meaning of grad phi. So this is diagram, and this is definition of grad phi. Now second one, we will discuss the physical meaning of divergence of any vector, divergence of a vector, that is del dot A. Second part, divergence of vector del dot A vector. So physically, divergence means to diverge, to spread like this. If any vector which is spreading with the distance, here the surface area, we consider surface area, number of lines are 4, but same surface area is drawn here, then only 2 lines can pass it. It means the flux is diverging. So physically, divergence means to spread in a space, divergence, diverge. We will consider this divergence by using the concept of flux. So I am taking or considering any cuboid like this, and here it is origin, it is x axis, it is y axis, and it is z axis. Let any vector is lying at the center of this cuboid. Any vector is lying at the center of this cuboid here. Let the flux is entering through this surface. Flux means number of lines. Flux means number of lines passing through the area. The flux is entering through this surface and leaving this surface. So net change in flux from this surface to this surface. Net change in flux we will consider net change in flux from along x-axis or along y-axis or along z-axis. It means number of lines passing through this surface and leaving at this surface. So net change in flux along x-axis. Similarly, number of lines entering through this surface at the bottom and leaving in the top surface. It means the change in flux along y-axis. Similarly, number of lines entering from backward surface and exit from front surface, that is along z-axis. So in all directions, we will consider the change in flux in all directions. So I am taking the example of any flux, let it is A. So what is flux? You know that flux is integral of any vector into ds. This is the definition of flux, total flux, or in short, the small flux is A dot ds or E dot ds. You know that any electric field or magnetic field or any vector dot multiply with ds, surface area. This is definition of flux. So we will consider the flux, the 3 cases of flux. That is, first one is along x-axis. Along x-axis means the number of lines passing through, entering from this surface and exit from second surface, left and right. So flux entering at left surface. So we may give the names to the surface, that is O, A, B, C, D, E, F and G. So first of all, I will consider this surface. Flux entering at left surface. Left means the surface O, A, B, C. O, A, B, C, this surface. Flux entering. And flux is leaving at this surface. Leaving means it will exit from that surface. So the net difference on flux leaving and flux entering is the change in flux within the cuboid along x-axis. So this is our task. Flux entering at left surface. So what is flux? Let at this point at center the vector is A vector. If we split this A vector into 3 components, then along x-axis component is Ax, along y-axis component is Ay, along z-axis the component of that vector is Az. So it is lying at the center. So from center this surface is at half distance. This is at half distance, it is again at half distance. So the left surface is at the half distance of the cuboid. So the flux entering at the left surface is equal to Ax minus, because it is on the left side and flux is decreasing along this side, Ax minus half of dAx upon dx into dx. Okay. This is the flux entering. Ax is at the center and Ax minus half, because it is on the left side, it is decreasing along this side. So Ax minus half of dx, dx by half, this is dx by half, basically half distance, and this is the rate by which flux is changing. So this is the rate by which flux is changing, and it is dx by 2, this is half of the distance. So this is flux entering at the left surface, that is OABC. Okay. This is first equation. Now the flux leaving the surface, the flux leaving at right surface, because it is entering, the flux on this surface is considered as entering, and flux is removing or going outward is taken as flux leaving. So flux leaving at right surface, and surface is DEFG, this surface, DEFG surface. This is Ax, because at the center it is Ax, and plus, because it is on the right hand side, flux is increasing, plus half of dx, okay, and the rate is again dAx upon dx. This is the rate. This is the rate of change of flux, the rate with which flux is changing with the distance, and it is dx by 2 is the half distance. Plus sign is because it is on the right hand side. Okay. So in first equation it is minus, in the second equation it is plus. The same factor is here, but it is minus, it is plus. Now net change in flux, net change in flux along x-axis. So the flux leaving minus flux entering, flux leaving minus flux entering. So that is Ax leaving means this one, plus half of this dAx upon dx into dx, and minus this one Ax minus half of this one, minus half of dAx upon dx into dx. So this is the difference between equation number 2 and 1. Equation number 2 minus equation number 1. When we will solve it, so Ax, this is, it will become minus Ax. So Ax is cancelled with Ax. Ultimately, this minus into minus plus, and half of 1. Ultimately, we will get dAx upon dx into this dx. This is the change in flux or area vector. Now by definition, I will apply the formula for area, because net change in flux is, this is dAx upon dx into dx into, this is the change in vector, dot area, ds vector, okay, ds area, because this is vector term in dot ds. So what is area of these two surfaces? So if this area is consisting of the dimensions y-axis and z-axis, because this area is consisting of yz, it is also yz. So this es become yz, and at last it will become dx upon dx into dx into dy dz, because the value of ds is dy into dz. because length into breadth, this one. In both cases, area is dy into dz. So overall, this equation become dAx with dx, it is differential term, into dx dy dz overall. This is third equation. This is change in flux along x-axis. Okay. Similarly, we will solve for y-axis also, because y means along this side, the flux entering from this side and leaving from this side, and the net change from leaving minus entering is the change in flux within the cuboid. So that change, I will not solve that change, I am writing the change in flux along y-axis. Change in flux along y-axis is dy on the same lines with dy into dx dy dz, because in this case dy upon dy and into dy, this is first term, and the area become dx into dz, because in both cases, the area vectors is consisting of this x-axis and this is z-axis, x and z. Length into breadth means x and z, and dy upon dy into dy, this is the same term which we will get in case of y-axis. So you do not need to solve for y and z axis. You may write directly the change in flux along y-axis and similarly along z-axis. Similarly, change in flux along z-axis, that is dAz upon dz into dx dy and dz. Sorry. Question number 3, question number 4 and question number 5. So these three change in flux which we will get in all cases. Now the total change in flux in whole cuboid, the whole we will consider along x-axis, y-axis and z-axis, in all cases we will add question number 3, 4 and 5, that is net change in flux, which will equal to, this is dAx upon dx, first one, plus when we add second term, it will become dy upon dy, and third term daz upon dz into dx dy dz is common. So this is net change in flux in whole cuboid. So we are considering all three parts, first term, second term, third term. I am adding these three terms and we will get this answer. So it will become, this may be written as the del dot A, because we have already solved the physical or mathematical equation for del dot A. Del means three components, A has three components. When we multiply these two, we will get this answer. So this is nothing, it is del dot A, and it is volume dV, because length into breadth into height, that is dV, volume. So overall, the change in flux is equal to divergence of A into dV, or we may written as del dot A is equal to change in flux over volume. So this is the physical meaning of the divergence. So divergence of any vector is nothing, it is equal to the change in flux per unit volume. So this is all about the physical meaning of divergence of any vector. Similarly, we will consider or we will study the physical meaning of curl of any vector in the next lecture. Thank you very much.